Start recording. All right, and so for everyone watching on YouTube, um, so there's going to be a continuity gap here because I lost the last three recordings when my hard disk exploded. Um, so we're going to carry on with episode, what's this, 46, but episodes 43 through 45 are going to be recorded later and or re-recorded, and so you'll hopefully have just watched those. So today's thing. Okay, so the first thing that we found, and we lost the recording of this, was that it's getting kind of hard to navigate through physicsgame.cs, and so one thing we can do just to make that easier is we can just grab the draw method and move it to the bottom of the file. That's just going to make it a little bit easier to navigate. Cause it's like, oh, I want the draw method, we'll go to the bottom. And the stuff in the middle is going to be a pain in the neck, but I kind of find that having like, all right, setup and then update at the top and then draw at the bottom just makes life easier. Oh yeah, Daniel, we might need you to zoom in slightly too at some point. Yeah. Okay. So what we were doing, we had this spring thing moving shapes around, and we could still do our separation. And we're just about at the point where we're going to do intersections and stuff and collisions and handle that like interactively. And so this is the last real opportunity to do something that I kind of wanted to look at some point, and it hasn't really come up. So what I'm going to do is I'm just going to scroll up here and set paused to true just for now. And so we should still have our shapes that we can drag around, and we can put in some circles. And so the thing, kind of the thing that brought this on is like if we overlap a whole bunch of shapes and we do a single separation step, what you find is that they all spew out quite far away from where they started. And so what we might want to do is set things up so that just like when we have two shapes, they separate perfectly. When we have more than two shapes, we might not be able to get them to separate perfectly, but it would be nice if we could get them to separate in a way that doesn't end up with them sort of scattered to the wind. Like it would be nice if they were like separated kind of a little bit, and maybe we could apply some iterative method, so we separate, and they eventually come out such that they're or more or less touching. And so you can imagine that might be useful if we were making something in the situation where lots of shapes could intersect at the same time, which may happen. So you can imagine if we have a like a corner, and we've got a ball's coming into the corner, it might touch both of them at once, and we want that separation to happen sensibly. So it might be something we actually want eventually too. So this is like one of those things where it's it's kind of like a thing where we need a creative solution.
Well, it seems to me like I'm kind of actually confused a little bit why that would happen with a bunch of overlapping objects, but it wouldn't happen with like two or three objects that are sort of not totally overlapping. Like it looks like it works fairly well in that situation. But what about the math is saying, all of you have to be so far apart from each other instead of trying to find the most I thought it was all about finding the minimum distance, but clearly these guys here are not minimally distant from each other.
Well, I mean,
And you're
that's an excellent question, and we can look at the source code. So if we scroll down and we find add shapes, and here we go, separation. And we go over to calculate separation. So we're adding pending separation, and that's going in there, and we look at calculate separation, and we look at what's being set, and what's happening is we're always accumulating the amount to separate. So the more shapes that are intersecting, the larger the pending separation will become.
right.
And so basically this is a creativity problem. It's like a
Yeah, I see. I mean,
yeah.
could we? Oh, sorry. Go ahead. You go ahead.
No,
There's a
I was
latency here.
reading my notes real quick. So yeah, so we want to sort of answer a couple of questions at first, and that is like sort of defining the problem, and like the different ways that it could, the different things that could be a problem. So, we want to eliminate the sort of over separation. But how accurately do we need to solve this? How many iterations do we want to do, and that sort of thing are important things to think about. And also, how much effort do we want to put into this is another important thing to think about. Like, we could come up with a really complicated mathematical solution, but like at the moment we're doing nothing. So what's like the next step up above nothing? And the other thing is possible cases to think about. So yeah, what do you think?
Well, I mean, the cheap idea is just, well, right now we're only tracking one separating vector. It might get out of hand, but maybe we need to be tracking the separations for each shape pair. Maybe that gets crazy because it's not really a pair. It could be a graph of multiple shapes overlapping. So that might get complicated. But it just seems like a smell that we've only got one vector that's tracking the separation. Oh no, we're not. No, sorry, I've misread the code. We're going in a for loop, but we're touching each shape as a pair, and then but only storing it in one container, which, like you said, we're always adding to.
Yes.
Maybe we need to reset that, or clear it out, or track multiple vectors.
So let's bring up the whiteboard, perhaps. Actually, we might not need the whiteboard. So one of the reasons that we're doing this is we're wanting to make it order independent. So if you have, so you can imagine if we allowed this to, and we've structured the code in such a way that it's actually kind of difficult to change it and demonstrate this. But you can imagine if we moved the shape while we're in the middle of this loop here, that will start to get interesting things happen. For example, if we have a situation like this, you can imagine that this is going to lead to some sort of weird result where they go around in a circle when you separate them, whereas what we really want is for them to sort of just move outwards a bit. And you can also see from that, we may need to iterate as well. And that's a viable solution because we'll have to be testing separation every single frame anyway. In fact, what we could do is
Seemed like we handled that situation perfectly just now.
yeah. So what I'm going to do is I'm just looking for the code that does this in update. Separation. Keys went down, so I'm going to try and change this to input.key is key down. So I'm just going to change this, and so if I make that little loop of stuff again, and now if I hold down S, you can see they spread out like that. But I'm left with this problem if I make this overlapping thing. If I hold down S, they all jump away from each other.
Mm-hmm.
So I mean, let's go to the whiteboard and sort of think about the possible cases we've got here. Let's see if the whiteboard is going to behave itself today.
Yeah, I mean, I guess I don't have the intuitive understanding why the overlap is causing a sort of explosion, whereas if you have them all touching each other in a circle, they're kind of doing what you expect.
So let's say we have 3 shapes. So 1 shape, 2 shape. How am I going to draw this? Here's a shape, and here's a shape, and here's the shape we're going to be looking at. And so what you can see is that they have this overlap here. And so what's going to happen is you're going to get a separation there, and then it's going to add a separation here. So we've got this case where this shape is getting separated twice in the same direction.
Right.
And what we really want is it to only get separated this sort of single amount. So that's the ideal case.
Yeah, it's the max of both of those vectors, but not the sum of them.
Yes. And then let's see if we have a situation like this. I'll draw that a bit better. So in this case, we've got this distance here and this distance here, so we're getting a separation that way, a separation that way, and the sum of these vectors is going to end up being like that. And so that's kind of fine because these ones will, like this will not move very much, and then these ones will move out in the opposite direction, and this one, so we can like simulate these 2 cases. So we've got that one and that one, and then if I make one here, so you can see this one's getting chucked out over that way, and it's oddly enough that one is because this one's overlapping. So that one's an interesting case. That's actually not too bad for this one. It's actually bad for this one, which is interesting. But then we have this case here, and so if we have like a line of these things, they tend to separate out okay. Getting separated perpendicular. So there's the. Unfortunately, I wrote this down like 2 weeks ago, and I've forgotten what the diagrams for this should be. But I remember I've got the text, but not the diagrams. Anyway, so if we've got like a perpendicular situation, what would that look like? So we've got contacts in this direction and this direction, and the addition of these will go out this way. And this is what we actually want. So we want them to add up in this case because we've got like that plus that equals this one coming out the middle. And so you can see we still want want to add them together in some way because we want,
Yeah.
like, we don't want to, oh, this is the longest one, so we'll go this way because that's sort of going in the wrong direction. So the other thing we don't want to do is start getting sort of weird results out of this. We still want to maintain the direction.
Right.
So I think the and we still, so the other case we want to think about, that's one, is we still want to maintain this, the pair case. So anything we do in a pair has to still separate out correctly as well. And of course,
Right.
this all has to keep working for triangles and stuff. Same, opposite, perpendicular.
So it's almost like you want to normalize it by some maximum distance. You want to keep the directionality, but you have to kind of recalculate how far.
Yes, and the other thing we want to keep is we want to keep the fact that like a small one will move more than a big one. So
Is that the toy mass bit, right?
that's the mass calculation. So that's these are all the scenarios that we have to take into account. So yeah, we have to keep the direction. We have to keep like the stuff that's already working perfectly. We have to keep the mass considered. And so it's basically the situation we need to deal with is if we have a whole lot of things overlapping, we don't end up with massive explosions of shapes. That's the problem we're trying to solve.
Right.
So, and so the question is, what do you think is the simplest solution to this problem that we could try?
Probably track all of the separations that those objects do separately, and then so you keep all of the calculations because you need them for all the reasons you just said.
Yep. So,
but then scale them so that they only go as far as the furthest one, maybe, or some value. So that not the furthest one, because that would actually make it worse. No, there's got to be a way to sorry, not the furthest one, the minimum distance, not the maximum distance. And that way you keep everything, but you can only go as far as the minimum separation for the smallest direction. And that's only, I guess, true if we're simulating, because we expect to have it tick the next tick. Like I don't think. What am I trying to say? I'm not sure if one of our requirements is that the whole thing gets separated on a single tick, and I don't think it is, because that's why we have the space bar, and that's why it gets a little bit better every time. So I think I think that would work. Track them all.
I think what we exactly. I think what we do want to maintain is like this one does separate on a single tick. I think that's probably worth maintaining. So you can imagine we couldn't do something like like a really simple solution would be to do here we go. So let me give you an example of like a really, really simple solution. So we could do this.
Oh, sure. Yeah, you're going to smooth that out over a billion steps.
And so you can see that this works.
Yeah.
But it has a lot of disadvantages. For starters, it takes a really long time to settle down. And the particular problem we get is like that case.
Yeah.
In fact, so you can imagine... Oh, sorry, you're going to say something?
No, it's just like, well, your whole game design is going to be impacted by that kind of decision, because now everything is sort of slow and squishy.
You can imagine the graph of like, this is the distance over frames. The distance being separated, it's actually going down like this. and so it never actually reaches 0.
Right. Xeno.
So yes, exactly. So this is why this case is important. So so you had an idea. So I think your idea was basically, let's do some kind of tracking so that we're basically saying, and what I'll point out, which could possibly save some time, is if we, we'll have to do a little bit more tracking for that to work, because we still have to add them up and go in that direction. So we're going to have to do some maths to maintain directionality.
Yeah, I figured you had to kind of leave the separations as they are, because otherwise you're just trying to go back and redo the calcs. It might be. I mean, I don't. It's just. Yeah, I think you kind of have to like do them all and then edit them all.
Yeah. So we can't simply save. We can't do what I was about to suggest, and then I was like, no, we can't do that. We can't go if like A move plus B move is less than, or if really separation amount is less than existing separation amount, do this. We can't do that because that's just going to select like one of these two arrows here, whereas we want to still do the addition and then scale it.
Yeah.
So, although
we can stack like an array of vector 2.
Well, what I will suggest is we probably want to avoid a situation, because you can see pending separation is coming in and it's the same length as the number of shapes. So at the moment we are order n, and that would be order n squared on memory.
Right.
And so if we have 100 shapes, suddenly we're using 10,000 memory slots.
Yeah, that's the problem.
So a solution that doesn't require storing n squared, or I mean, we could come up with some complicated list scheme, but we probably want to avoid that as well. So you can imagine that if we have here's our shapes, and then we have, right, here are all of the collisions, and then it's like, okay, here's our linked list probably of our contacts, and so one of them has 2 contacts, so this could be like this scenario here. So this one has color them, so it's like that one has contacts with green and blue. So hopefully my color-coded diagram makes sense.
Yeah.
So we could get around the this problem, and so that would be OM, which is M is basically the same thing as N, except we're looking at 2 different variables. So N is shapes and M contacts.
Right.
So,
is there a generally accepted solution to this?
That should be. So this is what you would do if you really needed to do this accurately. But obviously you can imagine this is quite a complicated thing to implement, and so like we want to do something really simple here. So the thing that we were doing before with like, times 0.05f, like that's maybe something more towards what we want to look at. And so...
Oh, I see. Maybe you just want to distinguish which ones you're allowed to smooth and which ones you're not, and just keep the ones you want to. Maybe you just want to. You don't want to smooth the ones that are only touching one object, but you do want to smooth the ones that are touching multiple objects.
Well, that's not a bad plan. Let's go to the web.
If we can determine that.
Well, we have a list of... so right now we have shapes, and they're coming in, shape, 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 shape. And then we have separation, and these are vectors, and they're coming in, and we've got an array of that. So we could track, count, for example. So count, 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 count. So every time we have one of these, so rather than tracking that, we could have, this is 2, this is 1, this is 1, this is 0, this is 0. And so this parallel array would just be ON as well, which is fine. So that's something we could do quite easily.
Yeah.
So how do you feel about that? I mean...
Yeah, I mean, I guess so. I mean, I don't know anymore. Like, I guess the idea is, are we trying to make we're trying to do a physics simulation, I guess, because we have things like mass and acceleration and so on. But the smoothing thing is clearly not based in physical reality.
No.
So it's sort of not.
Well, there's another advantage to this that I just thought of and that I will point out, and that is if we do it this way, we still have the separation vector, and that's going to come in handy later. So if you can imagine, if we have shapes that are the corner of something, and we have a shape coming in that's going to collide, and so it ends up here. Excuse me. And so it gets a separation out this way and out this way, and the result ends up being, well, it would be, up plus right is going to give us this direction here. And you can imagine this is going to be useful for calculating physics responses. And
for sure.
So just to give you an example of what that would be like, just a simple example would be two shapes colliding like this, and we get a separation out this way. And so you can imagine that this kind of looks like a surface like that. And so if we have a shape coming in, this is kind of what we're simulating, we have a shape coming in, we want it to reflect off that surface and bounce out. So this is like this is once we unpause the simulation, we've got our velocity vector. Hopefully that diagram makes sense. I'll redraw it later, but does that make sense? Daniel. Lost audio.
Yeah, I'm talking with mute on. That's what happened. I said, yeah, it makes sense why you want to keep the vector around, because you need to do things like the sum of them, because you need to determine the exit direction and with respect to velocity and everything. So yeah, it makes sense. We haven't gotten to that point yet, but
no.
I can see why it's necessary to keep the data.
So let's go and try it. Let's implement the count. Let's just count up how many collisions we have on a given frame, and we'll add the data in. And then once we have that data, this is kind of a useful approach. Once we have that data, we can, when we actually do the separation, we can, just combine them with whichever method we like. So in update we have shapes plus pending separation. So it can be like, uh, pending separation, and then intersection count. So I've started coding this, but I will hand it back to you and say.
That's interesting. I thought maybe that would only be in calculate separation, but I forgot. Yeah, we use these like working buffers here.
Mm.
We have axes in here. I was going to put the counting in here, but I guess you're right. We could use it somewhere else.
Well, what? Yeah. So that's actually an interesting point, and that is, you could put it in there, but then what you end up doing at the end, you would have to go for, shape count. So we've already got our for loop on the outside. So.
Right.
But that's a fair point.
Yeah.
So it could be in either place.
Well, not really, because we'd be doing a whole iteration. We don't need to.
Well, we'd lose the output is coming out pending separation, and we may want the original data outside the thing once we get to collisions.
Yeah, that makes sense. I was just trying to think about it more functional, because we talk about how we want to avoid state, but we're not really. It's not like we're storing this on different ticks or anything. So, yeah, fair enough. I will just use your name. Should be int, I think. Not ubit. Int. Int. And int. Oh. And then we'll put that in here. I think. Oh yeah, we'd have to count it otherwise. Oh yeah, we had the draw method too. It's gonna have to get the same.
Exactly.
All right. Okay, so I'm gonna increment this guy when we determine that there's an intersection. And I guess
I think that's about it.
yeah, right. I was just thinking about how to visualize it. Maybe we want to draw the number on the draw call for now to see if it's working.
Do we have text drawing set up?
Probably not. Yeah, I don't think so. I don't think we have a sprite font.
Let's have a look.
Well, we have
Oh, we know we do have a font.
large text. Yeah.
So I mean, we could do that if you like.
Mine's called large text. I think mine. I'm using like the
yours is
old
the
school
old one.
template.
That's all right. I think maybe it's not worth drawing necessarily.
Mm-hmm.
Or if we did want to draw it, maybe we wanted to just like, I don't know, draw a number of dots around the shape or something rather than bringing a font in. And
Yeah, that's
concerning
true.
ourselves
Well,
with
it's
that.
harder for me to do that. Maybe we'll just add an unit of opacity or something.
Well, what I might suggest is, I mean, let's test this work. This is the sort of thing where the thing's so simple. What I could say is maybe what we should do is we should run it, and stick a breakpoint there, And so let's just build up some very simple set of shapes so we don't have a whole lot of data. So maybe we have 1, 2, 3, 4, for example.
Mm-hmm.
And if we separate this, we can kind of predict what the result should be. So this one has 1, this one has
1,
2, this one has
2.
1, and this one has 0.
Right.
And so we'll just test if we got the code right.
Yeah, just hover over intersection count.
And of course,
oh, you can't do that kind of thing
it's
now.
memory, so that's fine. We'll add a watch, and let's bring my watch window up. So that's out of bounds, but that's fine. So, oh dear, 1. So 2. Now in C++, there's a way to do this, and that is, let's see if it works here. I think it's like that. Yeah. Unfortunately, the C# debugger won't let you just flat out watch an array of a certain length. Like this would just give us, 0 to 3. But unfortunately,
oh, that's cool.
It doesn't work in C#. So anyway,
well, we're right though. It works. So
yeah. Suffice to say,
the
code is fine. So let's just assume, because it's so simple and we just tested it, the intersection count is correct.
Mm-hmm.
So the next question is, what are we going to do when we apply it?
Right. So we basically we have two conditions. Well, I guess we have two conditions if it's greater than 1 and everything else.
Mm-hmm.
And in the case of when it's greater than 1, then we want to scale the pending separation value by 0.05 or whatever arbitrary number, and do nothing different if it's not greater than 1. Because it'll be 0. It'll be 0, or we want to separate fully, and the other option is we want to scale the separation by some value. So I think that works. If intersection count I is greater than 1, times whatever the scaling factor is. I don't know. That seems like as simple as it could be.
That is pretty simple. That looks pretty good. So we could just
might as well see it.
We just run it, and our drawing is going to be incorrect, but that's fine for now. So if we overlap a whole bunch of things, and then have 2 sitting on their own. So we kind of get to the problem where
it'll never. Yeah, I mean, I don't like it by any means. I mean, I think we're on the way to a solution, but I don't like how it's never gonna actually get in. Like, it's never gonna
terminate. Yeah.
It's kind of, I don't know. It's like any of those janky like physics simulators where the objects never settle.
Yes. So anyway, so that's not too bad. However, like, that's better than what it was before.
Right. It's that step up from nothing that we were talking about.
So really, the problem is this scaling factor. And can you think of anything we could do with that?
Yeah, I mean, well, we picked that out of the sky. Probably want to, let me think about it. Well, I don't know, would mass help? Like, maybe we want less scaling for smaller objects because they tend to move faster.
Well, that's actually not
yeah. Well, so the other thing would be, how do we get close? Like, how can we make a scalar that's actually going to end? Maybe it has a upper or an upper bound or something, and then it, um, or like I don't know. I mean, there's got to be a way to calculate this, the actual value that we could use, because we're trying to get somewhere. We're trying to like tween something. Um,
Well, okay, so there's a couple of interesting things we could do. Um, so mass is probably not the right thing to do, but we do have radius. So we could do something related to the shape's size. Now there's a small problem there, and that is if I run this, there's we'd have to do something sort of that's scale independent. So you can imagine if I make two shapes here, or three shapes, and then I zoom out, and then I make one, two, three shapes there. The radius is obviously very different. So we'd need to relate the radius in some way to the shape scale. So it's possible there's a solution down that road.
it seems like the wrong way, because now we're like incorporating like the viewers like kind of like externality, which seems like the opposite thing to do in a physics simulation. Should just kind of work
Well,
based on.
what we'd have to do in that case is we'd have to make it scale independent. So what we'd have to do if we went down that road, and I don't think we do want to, but we'd have to go uh, s equals pending separation I dot length, and then we'd have to do something like shapes I dot radius. And I don't know if I've got the division the right way around. Yeah, I think I do. So we could do that, and then we'd have to go math.max min 1. So, and the reason we do this is because then we maybe do this, and we don't want this to go above 1.0, because you can imagine that would be more separation than we have. So I mean, we could just, this is one of the things that you could do, is you just test if this works, and it doesn't, but it's a nice thought. Like we could 0.1. Oh, actually, see, this is the problem, and that is, as soon as you
You move the scalar now.
We're back. Yeah, we're back to the same place. The scalar's gotten smaller. I think that was working. You can see them pop out as soon as they hit 2.
It's threshold.
So I think that's working a little bit better, but it's maybe not the right solution. So, any other thoughts?
No, not really. I feel like we'd have to like have the actual, like, because if like there's obviously a correct answer where this should go. Like visually, it's easy to verify that, like, there's a minimum amount we should split, and I don't know. I don't like the idea of just slapping a scalar in there, but no, I kind of at the bottom of my idea barrel.
Well, that's fine. I mean, this is okay. So this is the sort of thing that you explore like this, and that's kind of the point of today's session. And this is, you kind of explore an idea like this, and then you basically sleep on it, and I know that in the past I've described problems as being like shower problems, and so it's like something you ponder in the shower. So I was thinking of giving you the solution that I came up with, but I'm actually thinking maybe I should leave you for a few days to ponder on it. What do you think?
Okay. Yeah, I'm happy to do that.
So basically, I will say that I think that this is the correct solution here, and the reason that this is the case is that it's really simple. It doesn't involve complicated lists or anything. It doesn't involve making a graph. It doesn't involve something that's n squared. So all we need to do
Yeah,
is
I feel like there's some kind of rules like we can apply to that eventually like where you like you were saying like it was just popping out. There's just got to be a way to use that simple counting to say, you know, do this while you're where we're not sure if we can make a definitive guess about how far to go, and then once you separate enough, we can because you're not touching one of those objects anymore. So yeah, I feel like there's an answer there.
The other thing that I will just really quickly do, and that is, now we have this count, we can do this. Shape being dragged. I just find the code. Okay, so we're calculating separation here, and we're drawing these sort of ghost shapes. So we can do this. If section count I equals 0, continue. So that might be something to just whack in at the end. And so the reason you do that is, hang on. We separate out, and then our like ghost things go away once we hit no collision.
Yeah, that's really helpful to visualize that.
So that's probably worth doing. So
Mm-hmm.
so yeah, if you want to just pop that in, I'll just check my notes and see if there's anything else I wanted to talk
sure.
about. Okay, I think that's pretty much all we wanted to cover today. So yeah, ponder on what you could do with all of the data we have here. So like what have we got? We've got. I feel like I'm slowed down navigating this. Here we go. Okay, we have the shape, and the shape itself has a position, a radius, a velocity, and some vertices. We've got the pending separation, which is a vector, and then we have the intersection count. And then, I mean, we probably don't want to use it, but we have things like the zoom factor and stuff that are global. And
yeah, I'm not sure I want to touch velocity either. I mean,
probably
that
not.
might be a pretty interesting way to do it, but we're not really simulating right now.
Exactly. So that's where we're at, and I think we'll leave it there. Thanks for watching,
Right on.
everybody, and